By keeping s-orbital and p-orbital in the mix, let's try to understand the basics of hybrid orbitals. Here this is s-orbital and this is p-orbital. The center of the p-orbital is the nucleus region, or it is region of node. Forgive me, it is singular node. A node is a zero electron density region in the 3D space which separates the two lobes of the p-orbital equally. S-orbital here has a completely shaded region, and whereas p-orbital is shaded with only one lobe and the other lobe is unshaded. The shaded regions in these two orbitals are represented by positive sign, whereas the unshaded region is represented by a negative sign. As of now, it is important to keep in mind that here positive and negative charge does not resemble any charge. As we know, the shapes of s-orbital is spherically symmetric in shape, which means that the probability of finding an electron at any particular distance from the nucleus is same in all direction. To put it in one word, we can call s-orbital as an isotropic. In case of p-orbital, there are three p-orbitals, that are px along the x-axis, py along the y-axis, and finally pz along the z-axis. So here in p-orbital, the probability of finding an electron is greatest along this x-axis, y-axis and z-axis. Therefore, you can say that p-orbital has a sense of direction. So when you're trying to find electrons, these electrons are mostly present on this axis, x, y and z. But in case of s-orbital, s-orbital is spherical, s-orbital is isotropic in nature. That means it is not dependent on any axis. It is unidirectional. Therefore, probability of finding electron is equal in all the direction. So we can conclude that p-orbital here is directional and s-orbital is not directional. When these two orbitals mix together to form a hybrid orbitals, the shape of these hybrid orbitals is completely dependent on the orbital that is directional. Here, in case of S and P, we have P as a directional orbital, so the shape of this hybrid orbital is completely dependent on the p orbital. Now we learned sp hybrid orbital is formed by mixing of s orbital and p orbital. If you see the hybrid sp orbital here, there is an important detail to be observed. The lobes of the hybrid orbital here are different in sizes. The lobes of the sp hybrid orbital is different in sizes. The left lobe of the hybrid orbital is smaller than the right lobe. The right lobe is the shaded region and the left lobe is the empty region. The reason for this can be explained by learning the fundamentals of mixing, that is how this s and p orbitals mixes. Firstly, let's take s orbital and divide s orbital into two equal halves. We know that density of finding an electron in s orbital is all over the orbital, that is maximum. So let's denote s orbital with the positive sign, and the left side of the s orbital is denoted by L for left, and right side of the s orbital is denoted by R for right. Secondly, imagine this p orbital in a three-dimensional view. and divide this p orbital into two equal halves at the center. The shaded region is at the top of the plane and the non-shaded region is at the bottom of the plane. If you see the shaded region, it is denoted with a positive charge because the probability of finding an electron at the shaded region, at the positive region, is maximum, whereas the probability of finding an electron at the non-shaded region or at the negative region, it is almost equal to 0. Now let's see how these orbitals mix. When left side of the s orbital mixes with the left side of the p orbital, that's gonna give you an destructive interference. And when the right side of the s orbital mixes with right side of the p orbital, it's going to give you a constructive interference. If you see clearly, when positive side of the orbital s orbital and negative side of the p orbital overlaps, I mean positive and negative overlaps, we get destructive interference, and when positive and positive overlaps, we get constructive interference. Constructive interference can be clearly explained by considering the wave nature of the electron. Here we have two different waves coming from two different orbitals. Both of them are represented with a positive sign on them. That means that these waves are coming from a shaded region of the orbital. If you see both the waves here, they are having the same starting point. And the first wave here is represented as wave X and the second wave is represented as wave Y. When two waves overlap on each other, a resultant wave is formed. Now let's draw the resultant wave on a new axis. In constructive interference, both the waves have identical wavelengths. So when these waves overlap, they merge each other on one top of the other exactly. Now let's see a few more details about the resultant wave. The amplitude of the resultant wave is much larger than the individual waves because the amplitude of the resultant wave is equal to the sum of their individual amplitudes. In wave X, look at the first peak. The height of this peak is called amplitude. Let's consider the amplitude of the first peak is 1 unit. Since wave X and wave Y are identical, the first peak or the amplitude of the first peak of Y wave is also 1 unit. Now if you see the amplitude of the resultant wave, it is nothing but the sum of the two individual amplitudes. So 1 plus 1 gives 2. If you repeat the same procedure with other peaks in wave X and wave Y, the resultant wave will always have the amplitude much bigger than the individual X and Y waves. We can conclude that in constructive interference, the resultant wave has a much bigger amplitude than the individual waves. Now let's see some important points to remember. Electron density. Constructive interference increases the electron density. Bonding orbitals. Bonding orbitals determines the shape of the molecules. The resultant lobe formed by the constructive interference carries the highest electron density, so the electrons involved in the bond formation are the electrons from the constructive interference. Since constructive interference resembles bonding electrons, whenever a new bond is formed, the energy of the electrons tends to absorb. So the new bonds bring new molecules, and the new molecules tend to have a lower energy than the individual atoms. Wave X and wave Y are said to be in phase because the crests and troughs are lined up in constructive interference. If two waves start at same point or in phase and travel the same distance, they will end in phase. In destructive interference, wave 1 and wave 2 does not start at the same point. So when these two waves overlap, the resultant wave formed is a null wave. In other words, you can say both the waves cancel each other in destructive interference. Now let's draw wave 1 and wave 2 on an x-axis and see why a null wave is formed. In destructive interference, when these two waves overlap on each other, they do not merge on each other exactly like it did in constructive interference. The reason for this thing is clearly both wave 1 and wave 2 are not identical waves. If you see here, the first peak of the first wave is in a positive region and the first peak of the second wave is in negative region. So the amplitude of the first peak will be positive 1 for the wave 1 and negative 1 for the second wave. The resultant wave is formed by adding these two waves. So positive 1 and negative 1 cancel each other and give you a null, 0. The amplitude of the other peaks in this x-axis gives the same null value for all other peaks. So you can conclude that in destructive interference, the resultant wave formed here is a null, or you can say both waves actually cancel each other. Electron density. Electron density decreases in destructive interference. The energy of the electrons in destructive interference remains high because these electrons does not participate in the bonding. Non-bonding. Let's see why destructive interference is called non-bonding. When two atoms tend to bond, there will be electrons that spend time close to the nucleus, and there will be electrons that spend most of their time outside the nucleus. Here you can conclude that the probability of finding electron in the destructive interference will also be decreased. In destructive interference, now we know that both the waves does not start at the same starting point. The resultant wave here is said to be out phase because the crests and troughs of this resultant wave are not lined up. Regardless of the distance traveled by this resultant wave, they are said to be out phase. In destructive interference, the amplitude of the resultant wave is much smaller than the amplitude of the original waves. When you represent hybrid orbitals in the form of lobes, you can observe that one lobe of the hybrid orbital is smaller than other one. The smaller lobe is the resultant lobe that is formed from the destructive interference, and the larger lobe is the resultant lobe that is formed from the constructive interference. Smaller lobe resembles that there is a less density of electrons in that region. We might get a doubt like, does all the central atoms undergo hybridization to form bonds? The answer is no. We'll find out the answer for this point in the next video, but for now, let's wind up this video by reading the definition of hybrid orbitals once. Hybrid orbitals is an orbital formed by the combination of two or more atomic orbitals. The resulting orbitals has a different shape and energy than the component orbital.